Hello, this is Kevin the TA here, and today I will be talking about different types of matter and how we can classify it. So, everything around you is matter. Your whole room or wherever you're watching this is made of matter. And matter is just anything that has a mass or volume. So, let's diversify more and see different types of matter. So, you can have a pure substance, and this means that every particle is identical to each other. So this can happen in many different ways. First off, you can just have an element, and if you have an element, a pure substance of an element, that means that that substance is composed of only one type of atom. So here, for example, this example of a balloon filled with helium counts as an element since it's composed of only one type of atom. Here, this bar of iron would also be an element since it's only one type of atom. And here we're getting to some oddities here. If you have O2 or Se8, so oxygen or selenium, these two are naturally bonded to itself in nature. So normally you'll see oxygen bonded to itself. So the two here represents that it's oxygen and oxygen bonded to itself, and here you have 8 seleniums. These are called diatomic molecules, and since it's only one type of atom in these two, they are still an element. So let's go over to compounds. Since it's different than an element, but also kind of similar. So if you have a compound is composed or has to be composed of two or more elements chemically bonded. So here, if we go down to the diatomic molecule example, you do have elements that are chemically bonded, but not two or more of different types of elements. So here would be an example of a compound if you had H2O or water, right? So here you can see we have two waters right here. And since we have two or more elements chemically bonded to itself and there are no imperfections, there's no other minerals in the water we have here, it's just pure H2O, it would be a pure substance. And this would be what we have written up here. This is the compound. And then let's just do another example here. Let's go down here to this substance Na3P3O9. So let's just draw that out real quick. We would have the sodiums here in the middle in purple. Then let's use orange. Orange for this phosphorus. So here would be the phosphorus. And then the oxygens, let's make them purple. So the oxygen would be purple and around here. So that's what Na3P3O9 looks like. So let's say we have that and we have 11 of them and they're just sitting in a beaker. Assuming that it's the only thing sitting in the beaker, then it's a pure substance, right? And it's a compound because it's made of two or more different elements chemically bonded to itself. So you can see here all of these are chemically bonded to each other and they're multiple elements. So you have Na here is one, phosphorus, and oxygen. And let's just quickly go over how to correctly write element names. If you're writing an element name, you need to have the first letter capitalized and second lowercase. So for example here, if there's many different ways you can mess it up, right? So if you have just F here versus FE, if you wrote lowercase f, that could potentially stand for something else than if you had it written as capital F, because capital F stands for fluorine and lowercase f, that could be in a different element as the second letter, right? So just when you're writing an element name, the first always has to be uppercase and the second always has to be lowercase. And then if it's just one letter, it's always going to be uppercase. So just follow this example. This is the first, this is the second. And then let's get into the last. We have mixtures here. They're the last type of matter. And a mixture, the way that you define a mixture is how well it's mixed. It's kind of arbitrary, but I'll go into how you have a well-mixed mixture and a not so well-mixed, also known as homogeneous or heterogeneous. Homogeneous means that it's well-mixed or almost perfectly mixed. A way you can remember this is homo. It means together, while hetero means different. So, as you can see here, if we have chocolate milk, let's say you buy some Nesquik chocolate milk from the grocery store. The way they make the milk is that milk is originally in many different layers since there's all sorts of different fat concentrations in milk when you get it from cows. So you'd have, once they do mix it though, after they get all the different layers mixed together, you'd have all the lactose together, you'd have all the water together too. And then let's just say that the X's, those are the sugar, right? So let's make those this nice purple color. If we dipped our finger in and we could look under a microscope and see all the different compounds that are inside chocolate milk, every single time we dip our finger in and look at it, we'd see the same general image, same amount of lactose, water, and sugar throughout. Whereas if you looked at a heterogeneous mixture, the reason why it's not well mixed is, for example, let's think of a garden salad. That's a perfect example of a not well mixed mixture or a heterogeneous mixture. Because if you dip your fork into a salad, you are not 100% guaranteed to get the same thing every time. If you go to Olive Garden and get a salad, the first scoop might be 3 pieces of lettuce, the next one might be a cherry tomato, a jalapeno, and a piece of lettuce, and the next one might just be all croutons. So imagine a mixture as if you're sampling that mixture, if you get the same result every time, no matter how many times you do it, it's homogeneous or well mixed. And if you'd get different results every time, for example, in a bag of Skittles, you aren't going to get the same color every time. That's going to be heterogeneous. Now let's move on how to properly do a chemical equation. So let's cross these off real quick. So do not pay attention to those. We will talk about those later. But right now we have the equation right here. H2 plus O2 is equal to H2O. So the only real criteria for making a chemical equation is that you have to balance it. So the number one thing in chemistry is that you cannot create or destroy matter. And what I mean by that is, let's label what we have here. We have H2, so hydrogen bonded to itself as drawn here. And you have O2, which is oxygen bonded to itself here. And then that double thing is a double bond, not the single bond here, but double bond that oxygen has with itself. And then you have the arrow indicating that these two combine to make H2O or water. That's drawn like this here. So we have two of the hydrogens, right? So those transfer over. Let's just draw a divider here. You have the two hydrogens, and let's make oxygen blue. You have the oxygen here, but if you see, you're going to be left with one blue dot all by itself. Now, this would be okay if the chemical equation said plus O, but since we do not have the plus O there, that means we are technically destroying matter, since you just have the singular oxygen here that isn't mentioned in the equation. So what you need to do is you need to add these 2's here. And the reason you do this is to balance the equation. So let's label it again. You have this time 2 of the hydrogen bonded to itself. So one here, one here. So let's just label it real quick. We have 4 of those. Then we go over to the other side. Let's go to this side here. And then we see that we have 4 hydrogens on both sides. So far so good. We haven't created or destroyed matter. It's been conserved. Then we have the oxygen here. And then as you can see, we have 2 oxygens, and then the 4 hydrogens we've already seen a match. So we can see here that because of these 2 coefficients out front, by changing the amount of hydrogen and oxygen we have, we can create the same amount of water on the other side. So another way of saying this is we have 4 hydrogens and then we have 2 oxygens, right? And then when you go out to the other side, it needs to be the same. You have to have 4 hydrogens and 2 oxygens. Obviously, they're bonded in a specific way, so you can't just write it this way. But that's the way conservation of matter works. Sorry, pardon me. Yeah, then let's go down here to the very last thing we need to cover for today, which is what a molecule is. A molecule is a particle composed of more than one atom. So, for example, if we have this definition here, right, everything up here in this chemical equation is a molecule, since it all has more than one atom, right? So since if we have helium here, for example, right, it's only one atom, since it's only helium. If it was helium-2, oh shoot, that was a bad 2, give me a sec. If we had helium-2 and we had it in subscript there that helium was bonded to itself, then that would be considered a molecule since it's more than one atom. But since it's singular, it's just an atom of helium. But anything else, for example, H2 would be a molecule, or CO2 would be a molecule. And it doesn't matter what type of atoms are bonded together. It doesn't have to be 2 of the same, 2 of the different. As long as it's over one atom, it is considered a molecule. Hopefully this is helpful. If you do need, you can always contact me or Mr. Schaefer. Well, yeah, this has been different types of matter, then also going over how to write and balance a chemical equation and what molecules are. Have a good day.